In this video, we're going to look at the atomic model and the nucleus. So we'll be looking at the structure of the atom. Atoms contain 3 subatomic particles, which are called protons, neutrons, and electrons. The protons and neutrons are found in the nucleus at the center of the atom, whereas electrons are arranged in energy levels at different distances from the nucleus. Right, the following is a table that shows the particle, relative mass, and the relative charge. The relative mass of a proton is 1. Relative charge is +1. Relative mass of a neutron is 1 as well, and it has no charge, it's neutral. The relative charge of an electron is approximately 1/1840, which we can round up to 2000, 1/2000. And its relative charge is -1. Atoms are electrically neutral overall, since the number of electrons is always the same as the number of protons. Atoms can lose or gain electrons to form ions. If an atom loses 1 or more electrons, it becomes a positively charged ion. On the other hand, if an atom gains 1 or more electrons, it becomes a negatively charged ion. Right, the alpha particle scattering experiment. This was done by Rutherford. Rutherford's alpha particle scattering experiment. Now that's the setup for the experiment here. What Lord Rutherford did is he bombarded a gold foil, which is shown there. That's our number 3 on this diagram. Bombarded it with alpha particles. So this is an alpha source, right? And then was detecting the scattered alpha particles along there. So it a movable detector to find out the scattering of these of these alpha particles. So in this experiment, a radioactive source in a lead box with a narrow hole is used. Alpha particles emerge from the hole in a straight line, so like this. The apparatus is in a vacuum chamber to prevent air molecules absorbing the alpha particles. Fixed thin metal foil is used. That's a gold foil. The detector is moved to different positions. That's number 4 there. The detector consists of a microscope focused on a small glass plate. Each time an alpha particle hits the plate, a spot of light is observed. The number of spots of light observed in a certain time is counted at each position. Right, let's look at the results of this experiment. Now, the results of the experiment are as shown here. The one shown in light blue is the electron cloud chamber, and then the one that's shown in golden color is the nucleus of the gold metal or element. The path shown in blue arrows here is the path of the alpha particles. So as you can see, this alpha particle path shows no deflection at all. This alpha particle path shows no deflection at all. This alpha particle path shows a slight deflection. Slight deflection here as well. Slight deflection here as well. Then here we have got an acute deflection, right? So in other words, the bounced back. And here again, bounced back like that. So that's the experiment, what they observed from the microscope. Now let's try and get the deduction from these observations. Now most of the alpha particles pass through without being deflected, so they pass straight through, like I showed you in the diagram. This shows that most of the atom is made up of space, so these alpha particles were passing through the empty space. Now of those alpha particles that bounce back, it means that there must be a small concentrated mass in the atom that is dense enough to make the alpha particle rebound. So the nucleus of an atom is dense. Then alpha particles changing direction is due to the fact that alpha particle is deflected by the nucleus, since the nucleus has protons which are positively charged. This showed that the nucleus of an atom is positively charged. Rutherford came up with the model of the atom called the nuclear model of the atom. We still use it today. Right, let's look at atomic number and mass number. Right, okay, before I do this, I'm going to show you a video again that is in conjunction with this video. I'll show you a video just on Rutherford's alpha particle scattering experiment. Atomic number and mass number. The atomic number of an atom is the number of protons it contains. All the atoms of a particular element have the same atomic number or the same number of protons. The mass number of an atom is the total number of protons and neutrons it contains. The notation used to describe each atom is this one, that's called the nuclide notation. X is the nuclide, which is the element. A is the mass number or nucleon number, and Z is the atomic number or the proton number. The example here is carbon 12. So carbon has a mass number of 12 or nucleon number of 12. So nucleons are those that are found inside the nucleus. So neutrons and protons, if you remember, they are found inside the nucleus. So they are called nucleons. So 12 nucleons and 6 protons. So 6 of the 12 nucleons are protons. So to get the number of electrons, you subtract the number of protons from the number of nucleons. So that would be 12 minus 6, which is 6. So carbon has 6 protons, 6 neutrons, and 6 electrons. Chemical properties of an element are controlled by the number of electrons in its atom. This is because the electrons are used to make bonds between elements. Atoms with the same proton or electron number have the same chemical properties because those same electrons involve themselves in bonding. Isotopes. Isotopes are the atoms of an element with different numbers of neutrons. They have the same proton number but different mass numbers. 3 isotopes of hydrogen are, the first one is the hydrogen that we know, which has 1 proton, 1 electron, and 0 neutrons. Remember, this being the nucleon number, subtract the proton number from the nucleon number to get the number of neutrons. The nucleon number is 1, so which means protons plus neutrons is equal to 1. And then the one below is proton number, so which means there are no neutrons there. And then the second one is deuterium. Deuterium has 2 nucleons, of which one of them is a proton, so which means it has 1 neutron. Then we've got tritium. Tritium has 3 nucleons, and one of them is a proton, so which means it has 2 neutrons. And in every case, the number of electrons equals the number of protons. Atomic equations. When writing equations For nuclear reactions, make sure that the total number of protons is the same before and after the reaction. The total number of nucleons is the same before and after the reaction as well. The example is given here of carbon reacting with helium. So we've got carbon, which is 12 nucleons and 6 protons. Add helium, which has got 4 nucleons, 2 protons. And to give you oxygen 16, which is 16 nucleons and 8 protons. So if you add the top number, 12 plus 4 gives you 16. Add the bottom number, 6 plus 2 equals 8. So this is always the case. Make sure that the nucleon numbers do balance. And then also the proton number should always balance. The total number of protons on the left side is always equal to the total number of protons on the right side. The same is true for the nucleon numbers because of the law of conservation of energy and charge. Now, lastly, I'm going to look at nuclear energy, fission and fusion. Energy and mass. According to Einstein, energy and mass are interchangeable or equivalent. So when you say interchangeable or equivalent, it means that if an object gains energy, its mass always increases. If it loses mass, its energy is released. So they are interchangeable or they're equivalent. Now the formula that governs this is delta E is equal to delta mc squared. The famous equation, E is equal to mc squared. So converting your mass into energy, you need to multiply by the square of the speed of light. 3 times 10 to the power of 8 squared, right there. Fission. This is the splitting of a uranium-235 atom into 2 smaller atoms when a neutron penetrates it. 2 or 3 neutrons are released which may hit other uranium-235 atoms, causing them to split, and release more neutrons, causing a chain reaction. However, the uranium-235 must be above a certain critical mass for a chain reaction to occur. So let's study this. So this is the uranium bombarded by a neutron. So it's going to form these other nuclides, right? Or rather radioisotopes. And then you bombard these, you form these 2 neutrons. The 2 neutrons are used again to bombard the uranium, and then you form other 2 neutrons this side and the 2 neutrons this side. So as you can see that a chain reaction is started. The mass of the uranium atom before the reaction occurs is greater than the mass of the product of the reaction. The mass lost is changed into energy according to Einstein's equation above. Right. Then lastly, we are going to look at fusion. Nuclear fusion is the joining of 2 light nuclei to form a heavier nucleus. It is the process by which energy is released in stars and the sun. In the sun, light hydrogen nuclei fuse or join to form helium nuclei. There is a reduction in mass. When this occurs, and energy is released by the equation above. Okay, so the equation of if we have 2 hydrogen atoms combining to form 1 helium nucleus. Okay, and large sums of energy is released in the process. The energy is released as electromagnetic waves which reach the earth as light and heat radiation. For a fusion reaction to occur, very high temperatures are required, about 10 to the power of 6 kelvins. Currently, the challenges that we are having are having a vessel that can withstand this great temperature. Right, so let me know in the comments section whether you understood the topic or you need further clarification on some parts. Signing out.